Thank you, Asu, and thanks to MIT and IDSS for inviting me to be here. It's quite an honor, and I appreciate it. I have to tell a little bit of a story here. Rick Ross sent me an email before the event and told me that I was fancy schmancy because I was on the program. So I got dressed up and wore a suit and tie. This is what we do in Washington. And about 20 minutes ago, Simon Johnson delivered the bad news, which is that, and this is bad news for some of you in the audience too, is if you show up at the Media Lab wearing a necktie, you're sending a strong signal that you're completely clueless. Just so you know. Okay, big data challenges and opportunities in financial stability monitoring. I don't think I'm going to tell this crowd anything about big data that you don't already know, at least big data per se, but hopefully I'll map some of those issues to financial stability considerations, and that might be news. I have to do a disclaimer because I do work for the government. Views and opinions expressed are those of the authors do not necessarily represent official OFR Treasury positions of policy. Done. For those of you who are taking snapshots of the slides as they go by, actually pretty much all of this is in a forthcoming paper that's going to be the Bank of France Financial Stability Review is going to publish in a week or two. And those are my co-authors on that paper. So Jag is at Michigan and Luik is at Maryland. A little anecdote. I several months ago had the pleasure of chatting with Roger Myerson, who won the Nobel Prize in Economics several years ago. He came to the OFR for a visit, and his work is in game theory and the economic theory of information. And in the course of that conversation, I had this little epiphany that his research is all about information theory. A lot of the stuff I work on is about information reality. The issues here around big data are implementation issues, and a lot of times in economics we sort of sweep that under the rug. But working for the OFR, we have to deal with the implementation realities, and they matter. So the four V's there. I think you're familiar with those. They're all basically scalability problems. We point out in the first paragraph of the paper that big data is a misnomer. A data set is not big. It cannot be big, is sort of the point. A data set is too big for a particular use case with a particular implementation technology. So just the same way that my shirt is not too big, it's too big for me. Is the way to think about it. And there's a great quote there from Bani Banerjee, you can't solve exponential problems with linear solutions. It gets to that point. You got to fight computation with computation. Basic structure of the paper in these slides is we work through a data life cycle from a financial stability monitoring perspective. This life cycle would apply at this level of generality to pretty much any organization. Data acquisition, data cleaning, integration and representation, modeling and analysis, and data sharing and transparency. And what we do in the paper is, and in the rest of the talk, is map these issues to specific examples in financial stability monitoring. The ones I'm going to focus on here may not even be the best examples to use, but they were ones that were pithy and I could talk about quickly. They're certainly not the only examples. So, starting from the top, data acquisition. One of the key facts about financial stability monitoring is that the financial system is big. It's really big and really diverse, and you really can't and don't want to monitor everything all the time. So you need some mechanism for selective monitoring coupled with a mechanism for resolution enhancement when you need it. You need to be able to drill down. And there are four key dimensions that we see in which drill down is important. So first is coverage. think of a Google Maps analogy. Does your mapping technology allow you to maneuver around the landscape and cover everything as you need it? And we point to the G20 Data Gaps Initiative that began after the crisis, when the question of coverage in the shadow banking system became very prominent. Frequency is a second issue, and to some extent, you can use temporal quadratures to refine your picture. To some extent, you can't, because as frequencies increase, things like measurement noise and microstructure noise become more and more prominent, and there are limits, and especially with high-frequency trading, that is an issue. So the paper by Lombardi, he's a temporal measurement expert at NIST, points out that the FINRA timestamp requirement is on the order of a second. The trading latency in high-frequency markets is 3 orders of magnitude finer than that. Granularity and detail, these are frequently confounded. Granularity we're thinking of as the level of aggregation. So think about aggregate operators across the rows in a database, and detail is the set of attributes. So think of the columns in the database and what's available there. One example of what can go wrong with resolution enhancement. This is a paper that Phil Monin and I at the OFR published recently on risk measurement precision in Form PF, and that is a data collection to capture risk exposures in the hedge fund industry. There's no resolution enhancement built in, so there's a fixed set of buckets. And the funds are supposed to report risk characteristics on exposures in those buckets. So, for example, the top 5 counterparties, what's your aggregate exposure to them? And the basic question we ask, and this was partly motivated by the fact that the PF data are highly confidential, and we didn't want to go through the legal hassles of addressing this question, so we didn't use actual data. What we did was we created our own simulated hedge funds, had them fill out Form PF, and then we calibrated the portfolio weights on these hedge funds. We had tens of thousands of these simulated funds. We calibrated the portfolio weights so that all of our portfolios looked identical on Form PF. And then we asked for all the other dimensions, risk dimensions that you might measure, given that they are presenting a fixed picture to the SEC, how much variability could there be? And that's what this picture is. Well, the little equation here is the bifurcation between the risk measures, everything you might want to know, all the details, and split that into the things that are reported on Form PF, the things that are not. And what the picture shows you is the cross-sectional variability among the things that are not reported on Form PF, given that all these thousands of firms are identical on PF, and you can see it's significant. Okay, moving on to second step, data cleaning. It's easy to ask the question, why is there a scalability issue in data cleaning? Isn't data quality sort of linear in the volume of data? In one sense, the answer is yes, but it also depends on the process that you're pushing the data through. So a little thought experiment here. So this is a picture, time series plot of mortgage data starting in the early 90s and going through the crisis. You see charge-offs, delinquencies, and the heavy line is foreclosures. And there's an order of magnitude increase in the foreclosure rate during the crisis. And so a little thought experiment I'd ask you to do is imagine that you're driving down a highway. You're the only car on the road. It's not a challenging driving situation. So you're driving at a safe speed, let's say 50 miles an hour. And now imagine an order of magnitude increase in the speed of your car. What do you think will happen? And the answer is you won't be thinking. You will be dead because your car will literally fall apart and you will perish in a fireball. And that's sort of what happened, if you remember the robo-signing crisis in the wake of Lehman. So this was a very clever cartoon from the Washington Post on rubber stamping the foreclosures on mortgages. And we just point out here that the robo-signing crisis is one of many. A particularly juicy one for me, I have an interest in history, is the Civil War greenbacks was sort of the first robo-signing event in U.S. financial history. The Treasury started issuing large denomination debt to finance the war effort. Quickly discovered that they had exhausted the large investors and started issuing smaller and smaller denominations. And the little signatures on your dollar bill, those used to be actual signatures of the Secretary of the Treasury. They invented the law and the physical machinery to do that automatically, and for about 20 years, the main Treasury building in downtown DC was basically a printing plant to robo-sign greenbacks. Here's a biggie for us. This is the next phase in the process data integration and representation. Again, the financial system is big. It's also very diverse. And so we have a tremendous data integration and semantic integration issue. The very simplest, most basic, most important part of that is identification. And that's where we've started. So the OFR was instrumental in initiating the Global Legal Entity Identifier Initiative. And for folks in this room, this should be old hat, but there's a very basic network effect here. You see a significant complexity savings by moving to a centralized identification scheme. I'll also point out, the opportunity to participate in the challenges have closed, but the OFR has teamed up with NIST on a grant to solicit automated data alignment techniques for identification schemes through this FEIII Challenges event, and we'll be announcing those results this summer. Next phase, data modeling and analysis. It's easy to think that more data is always better, and econometrics shouldn't be happier, but it turns out that even here, the implementations issues raise their head. So this is one example, the fat regression problem. This is, in large data sets, you can do all kinds of feature extraction and expand the list of details. If the list of details, that's the number P, exceeds the number of observations significantly, it turns out that a lot of basic asymptotic theory underlying econometrics starts to fall apart. So the data are distributed sparsely in too big a space is the basic problem. So Donahoe and Stodden here, this is a picture that I swiped from paper of theirs. They derive the theoretical results. They're basically, this is a Monte Carlo analysis. They're looking at model selection. Which coefficients are you going to measure? They use a lasso technique to do variable selection. And that sort of sigmoidal black line in the middle is the theoretical transition point. And then the colored areas are the actual Monte Carlo results. You see that the actual results follow the theoretical prediction pretty closely, is that as the observations get more and more sparsely distributed, the model selection accuracy falls apart pretty dramatically. And my last one is sort of the final phase, sharing the data at the end, transparency. This was a picture that I took from a paper that on market liquidity measurement that I'm working on with some co-authors at the OFR, John Lichty and Tom Piontek. And what we're doing here is trying to measure market liquidity on a daily basis from a broad set of markets. We do some dimensionality reduction there, so we take tens of thousands of corporate bonds and thousands of equities and combine those into portfolios. And then each portfolio is a ribbon. The upshot here is that what you're looking at in this picture is 250,000 data points. So it is, in fact, possible, if you're a little bit clever, to squeeze a lot of data into small space with visualization. And that's it. Thank you.